So we're going to use two very simple properties about these subsets in order to develop an algorithm for efficiently counting. So for example, if the set K is not big enough, meaning if we have a certain set K and that set K does not appear in the fraction T of the baskets that we're looking at, so the probability of K is less than T, then we immediately know that any subset K prime that we can construct by taking K and adding another object to it, another element. So we take K union with some other set A, is also not going to be big enough. So in other words, if P of K is less than T, then we know that the P of K prime has to also be less than T. So for example, if K is equal to A and B, and if these items appear together in X baskets, then the set of items A, B, and C have to appear in less than or equal to X baskets. If we have X baskets that contain both A and B, we can't have more than X baskets that contain A, B, and C. This is simple logic, and that follows because the set K is a subset of the set K prime. Mathematically, what that means is that we can write the probability of the set K prime as the joint probability of the set K and the set A, where these two sets are disjoint. We can write this joint probability as the conditional probability of A given K times the marginal probability of K. Because a probability has to be less than 1, we know that the product of these two numbers must be less than P of K. We take P of K and multiply it by a number less than 1 that has to reduce the size of P of K. So the product of these two numbers has to be less than or equal to P of K. If this is 1, then it would be equal. And since we know that P of K is less than T by assumption, we therefore know that P of K prime also has to be less than T. So this means that any set K that we know occurs in fewer than the fraction T of the baskets, we can avoid having to construct any larger subset K prime that contains K as a subset of that larger set. So we can immediately eliminate a lot of checking. By the converse, if P of K is greater than T and A is a subset of K, then we automatically know that P of A has to be greater than P of K, has to be greater than T. So if K satisfies our threshold, then all subsets of K have to also satisfy our threshold. That's the kind of the inverse of this of the first logical rule. So the first property says this: if A and B don't co-occur enough times to pass our threshold, then we can immediately eliminate all of these other subsets that contain A and B in them. So all of these sets that contain A and B as part of that set, we immediately know that any of these subsets also will not occur enough times to pass our threshold. So this is the first property. If we eliminate this set, we immediately can eliminate all of these subsets for checking. The inverse property of that says that if, for example, the set CDE co-occurs enough, so if objects C, D, and E occur together enough times to be above our threshold, then all subsets of C, D, E also must co-occur together to satisfy our threshold. So if C, D, E appear in enough baskets together, then C and D also must appear in enough baskets together, because the probability of all of these subsets has to be greater than the probability of this subset. So this leads us to the most basic version of the a priori algorithm. So this can be improved in different ways to make it more efficient, but already we've made quite a bit of progress by reducing the 2 to the p different sets we have to check to something that can actually be done in a finite and in a reasonable amount of time. So first, we're going to set some threshold, n times t, where t is a number between 0 and 1, but it's relatively small enough that we don't expect there to be many subsets that co-occur together more than n times t times in our data set. The a priori algorithm then has one iteration for each size of subsets that we might want to check. So in the first kind of step, we would want to check all subsets of size 1. So in this sense, we're going to take every object and we're going to keep all of those objects that appear in more than n times t baskets. So those are all the sets of size 1 that occur frequently enough. Those are the objects that are bought frequently enough that they have more than n times t purchases among the n total purchases. Then at step 2, we want to check all of the subsets of size 2. In this sense, we're going to take all pairs of objects that have survived step 1. And so this is where the properties that we discussed come into play. If something didn't pass step 1, then taking a set of size 2 containing one of those objects is not going to occur enough. So if the third object doesn't appear in more than n times t baskets, then the third object plus the fifth object isn't going to appear in more than n times t objects. We immediately know that, so we don't even have to check it. So we take all of the sets of size 1 that pass this threshold and construct subsets of size 2 among those objects, and then check those and see which subsets of size 2 appear in more than n times t baskets. And keep the ones that appear more than n times t times, and then throw away all subsets of size 2 that don't occur enough times. And then we keep doing this. For example, once we get to subsets of size k, what we do is we take all subsets of size k minus 1 that passed the threshold, that appear in more than n times t baskets, and then we add a new object by incrementing each of those sets of size k minus 1 with an object that survives step 1, but not already in the set, to make a set of size k. We then construct that potential set of interest of size k. We check in our data set whether or not that set of size k appears more than n times t times. If it does, we keep it. If it doesn't, we throw it away. So it's still a brute force search, but it's reducing the amount of searching that we need to do by not fruitlessly searching. We're only searching subsets that could potentially be of interest, things that we a priori know are not going to be of interest, that they won't satisfy this threshold. We don't even bother checking. And so it should be clear, intuitively speaking, that as k increases, we can hope that the number of sets that pass on to the next size k plus 1 is going to be decreasing. So as k is increasing, we're having fewer and fewer sets that satisfy this threshold, and at a certain value of k, no sets are going to survive. So at a certain value k, much less than p, we're not going to be able to find any subset of that size that occurs in more than n times t of the data points that we have. At that point, we're done. We don't need to check any sets of size larger than k, because we know that they can't exist. So that's the a priori algorithm. That's the steps that we follow for checking whether different subsets appear more than fraction t number of times. Now the question is, does this algorithm check every subset? So we're going to assume that if we present a subset for checking, then we follow the brute force counting. We literally go through all n objects that we have, all n data points, and we check whether that particular subset appears in each one of those data points and count the number of times it appears. We then divide that count by n, and if that fraction then is greater than t, we keep that subset. If it's not, we throw it away. So we're going to assume that we can find that if we're presented with a subset, we'll be able to then verify whether it's something we should keep or not. So really the only question is, will we check every subset that passes this threshold. So the proof is fairly straightforward, and it's a proof by induction. So we're going to assume that we know every single subset of size k minus 1 for which the empirical probability of that subset is greater than t. Then we need to show that if we know every subset of size k minus 1, we're going to check every potential subset of size k that could possibly have empirical probability greater than t. And so let's look at this through an example of subsets of size 3. So for example, assume that we know that the set A, B, and C appears in more than n times t baskets. The question now is, will we check it? So if we know that A, B, and C appear in more than n times t baskets, we know that all subsets of this set of 3 objects has to also appear in more than n times t baskets. So for example, we know that A and B have to appear co-occur in more than n times t baskets. We also know that C has to appear in more than n times t baskets. So by assumption, again, we want to prove for k equals 3. By assumption, we're going to assume that we found the set of size size 2, A and B, and we know that this set A and B appears in more than n times t baskets by assumption. So we know that this set satisfies this, this threshold. From the a priori algorithm, because the first step checked all subsets of size 1, we also found the set C, and we know that this set also occurs more than t fraction of the baskets. So we're going to check the union of A and B with C. So we know that we will check A and B and C when at the third step in this algorithm. And so now we follow by induction. We know that we have all subsets of size 1 by the brute force search. And by induction, we therefore know that we have all subsets of size 2 by brute force search. And therefore, because we know we have all subsets of size 2, again by these rules, we know that we have all subsets of size 3 and so on. So it's an inductive proof. So I want to point out that as written, the a priori algorithm can lead to duplicate sets for checking. So for example, if we have the set A and B and the set C, we can take their union. And also if we have the set A and C and the set B, we could take their union, but those two sets are the same. So we could actually, by the a priori algorithm, check these two sets as if they were different sets, when in fact they're the same set. So indexing methods can be used to make sure that we don't do this. Also, for each proposed set K, should we iterate through every basket for checking? Again, there are tricks that we can use to make this faster that take structure into account, so we don't have to actually iterate through all n baskets to check whether a proposed K appears in that basket or not.